Hi Kumar. Hi.
Sorry, Sreejith.
Oh, I was just saying hi to Kumar.
Oh, okay,
Okay.
okay, okay.
Madhukar here.
Okay. Okay,
Okay, I
ठीक है,
think
let's get
we're
started.
recording. Yeah, you can.
Shall
Okay,
we
ठीक है.
start or?
Yeah.
Okay, so welcome everyone to this talk. It's a pleasure to have Sreejith with us. Sreejith is a faculty member at IIT Goa, and his research interests span automata, logic, complexity, and more recently, formal methods for ML. So today, Sreejith will tell us about learning deterministic one-counter automata. Over to Sreejith.
Yeah. Good evening, everyone. Thank you for inviting me to this IARCS talk. So I'll be presenting this work on learning deterministic one-counter automata. It's a joint work with Prince, um, uh, Dr. Prince, because he recently got his PhD degree, and also Penel and myself. So let's start. So first of all, what's an on-counter automata? So an on-counter automata is there's a finite state machine and a counter. So there's this one counter which the finite state machine can increment, decrement, or not change the counter value. Now there's one more thing quite important, which is that a finite state machine can also see whether the counter is zero or not. And based on whether it's zero or not, it can decide where to move. See that it can only check whether it's zero or not. No other comparisons or anything like that is possible. Okay, so this is the definition of a non-counter automata, and then you can have if the machine is deterministic, it's a deterministic one-counter automata. It's a non-deterministic. The finite state machine is non-deterministic. It's a non-deterministic one-counter automata. Now, here's an example of a non-counter automata. We'll just quickly see what it means. If you notice here on so on the edge, uh, there's a self loop on P with A greater than or equal to 0 and plus 1, which means that you can take that edge if the current counter value is greater than or equal to 0 and you see the letter A, but then you increment the counter by plus 1. Now you can take this edge if the counter is strictly greater than 0, not equal to 0. You can only take this edge if the counter is strictly greater than 0 and the letter is B, but then you decrement the counter. Similarly, you can read the rest. So here this says that A, you can take this edge if the counter value is exactly 0 and you see the letter A, but then you increment the counter by 1. Okay. Now notice that the syntactically it's forced that the counter never becomes negative. Yeah, so the counter remains 0 or greater than. So the counter does not go become a negative number. So this is a definition of an on-counter automata. So now you can see that this defines the language. So this recognizes the language A raised to n, B raised to n, A. How does it do? So basically in this loop, you can keep on taking A. If you see an A, you basically take this edge and you keep on incrementing the counter. So if you see 5 A's, your counter will become 5. Then you see a B, the counter is decremented by 1. Then you see sequence of B's, your counter will again decrement. Finally, once the counter reaches 0, you can take this edge A. So therefore, this recognizes the language A raised to n, B raised to n, A. I hope this is clear. So this is the model we are going to be interested in. And so you can see that on A, you take this edge and then the counter is incremented. Another A, the counter is again incremented. On B, the counter comes down, counter comes down again, and the final A is taken when the counter is 0. Okay, so this way it recognizes the language A raised to n, B raised to n, A. Now, so just to conclude, so there is a final state. Here the final state is R. This is start state, which is recognized by this incoming arrow P. So standard automata usage notation. Okay.
So,
Now,
Sreejith, I think Prahlad wants to know if you can, do you allow epsilon transitions?
yeah, so actually in deterministic on-counter automata, you allow epsilon transitions. So in this work, actually we allow epsilon transitions, but I didn't want to confuse everyone with epsilon transitions. So we'll just restrict our model to, in this talk, we'll restrict it to what is called as a real-time encounter automata where there are no epsilon transitions. But the work basically also deals with epsilon transitions. We can, once we finish, we can just discuss what to do when you have an epsilon transition. Okay. So, so why what are the motivations for studying on-counter automata? So firstly, it's a strictly it's a strict superset of finite automata, the kind of expressiveness, the languages it can recognize, and it's a strict subset of push-down automata. Now, so like, we use these machines to model systems or software. So finite automata is used extensively in hardware verification, etc. On the other hand, push-down automata can model softwares and highly complex systems. However, if you notice like the algorithmic complexity of finite automata is like most of the algorithms like equivalence test, etc., are linear for finite automata. On the other hand, for push-down automata, it becomes quite difficult. I'm talking about deterministic push-down automata, it becomes quite hard, and non-deterministic, it becomes undecidable. On the other hand, for one-counter automata, problems are some of the problems are theoretically good, however, practically may not be feasible as of now. So, for example, the major challenges in on-counter automata is I'm talking about explicitly about deterministic on-counter automata here. So, in this talk, we'll be dealing with deterministic on-counter automata. Even if I'm using OCA, I'm mostly be talking about deterministic on-counter automata because most of the problems for non-deterministic OCAs are undecidable. So, so major challenges in deterministic OCA is the equivalence problem, which is it's polynomial, but it's very bad as of now. It's not practical. O of n raised to 20, and the active learning algorithm, which we'll soon see, is currently exponential. That's so. These are the two major challenges in OCA. Now, so let's see what is the active learning framework, which is basically the talk is going to be of active learning of DOCA. So in an active learning framework, there are going to be two parties. There's a learner and there's a teacher. So the teacher knows a language of a DOCA. Okay, and that DOCA we are going to denote it by T, basically teacher's DOCA T. And the learner wants to learn a DOCA L such that T and L are the same. Okay, so basically T and L accept the same language. It may not be the same DOCA, but it accepts the same language. Now, the learner can ask some questions to the about the language to the teacher. Okay, and the teacher answers those questions, and based on those answers, the learner is trying to build this DOCA L. So this is the active learning framework. Now, what kind of queries can usually learner ask the teacher? Now, so this is one interesting question is membership query. What is membership query? So the learner asks, okay, I give you a word W, is it in the language? And so the teacher, you see that the teacher knows in her mind, there's a teacher knows a DOCA, and now the learner is asking is W is in that language. Now the teacher says yes or no. So the teacher is supposed to be honest. She's not going to fool the learner, so she is going to be honest. Okay? So she will correctly say yes or no. Next query is another kind of query is equivalence query, where the learner gives the teacher a DOCA and asks, is this DOCA equivalent to the DOCA in your mind? Or now the teacher says yes. So if the teacher says yes, basically you have learned, the learner has learned the language the teacher has in her mind. Or the teacher will say no, and the teacher gives a counterexample W that distinguishes L and T. Okay, where T is the DOCA in the with the teacher. So keep in mind that in general the teacher need not know the DOCA T. She needs to know only the language T. So that's the ideal setup we want. But when we talk, we'll just say that the teacher has a DOCA T in her mind, so that it's more easier to explain things. However, technically the teacher knows only a language. Now there's another kind of query which is basically called as minimal equivalence query. Here again learner gives a DOCL to the teacher, and the teacher now says yes, this is the language I have I have in my mind, or she says no. However, the teacher returns a minimal word W that distinguishes L and T, which is basically in the symmetric difference of L and T. You give the smallest, you return the smallest word. Yeah. So basically the smallest word which distinguishes them. So this is a minimal equivalence query. Another query is counter value query. Here the learner gives a W to the teacher, and the teacher and asks what is the counter value you see on reading W, and the teacher returns the counter value W. However, so this query, as you can notice, is dependent on a particular OCA. So the teacher, not just the language, the teacher should know also the DOCA in her mind. So this is like a syntactic. This provides syntactic information. So these are standard queries in this being used in this setup. Now, what is our result? So our result is the following. So let the teacher know a DOCA language, and let's assume that T is a minimal DOCA that accepts that language, and N is the number of states in T. Then the oil star algorithm learns a DOCA-L that is equivalent to T in time polynomial in N using membership and minimal equivalence queries. So the two queries used, membership and the minimal equivalence query. Just to recap, minimal equivalence query is you also you provide a hypothesis DOCA to the teacher, and the teacher returns the smallest word which distinguishes L and T. Okay. So this is the result. So we'll see the proof of this.
So Sreejith, Madhukar here.
Yeah.
So you said that equivalence is polynomial but n raised to 20.
Yeah, equivalence is n raised to 20. Yeah, it's polynomial but n raised to 20.
And minimal equivalence?
Yeah, that's also n raised to 20.
Okay.
Yeah. So basically, yeah, minimal equivalence also n raised to 20. We can, I mean, we can discuss the proof of it later. I mean,
okay.
Just not to deviate from the topic. Okay, so so that's the Now, what do we know as of now? So basically, the most famous result in this framework is by Angluin in 1987. She showed that DFA when you have can be learned in polynomial time using membership and equivalence queries. Okay, and then a host of results on uncounter automata. So Fahmy and Roos worked on deterministic uncounter automata, but it's real time, so which is a strict subclass of DOCA, basically the one without epsilon transitions. And they used membership and minimal equivalence queries and gave an exp time algorithm. Nader and loading showed it for visibly uncounter automata, again using membership and minimal equivalence query and exp time algorithm. Brewer et al. In 2022 showed that you can learn again real-time DOCA using membership, minimal equivalence, and counter value queries. So it's kind of it basically takes the ideas from Nader and loading, which uses visibly, because visibly you know the counter values. So along with counter values, Brewer gives a learning algorithm, which is again exp time algorithm. Then later we had work where we use membership, minimal equivalence, and counter value queries. However, that's also explained because we use SAT solvers, and however, the number of queries is polynomial, even though the running time to learn is explained. So note that all this time is this exp time p etc. is a function of the minimal machine which recognize the same language. So I hope as of now things are clear. So now let's look at the one technical part of the talk. So basically we want to understand what is the configuration graph of a DOCA and some properties of it. So what is the configuration graph? So a configuration is a pair P comma I, where P is a state and I is a counter value. And what is a configuration graph? In a configuration graph, basically the states are all configurations of the form P comma I. Then you have an edge from P comma I to Q comma J. If there is a transition from P to Q on letter A, and the counter value changes from I to J. Okay. So this is based on the transition rule of the DOCA. Then final states are all P comma I, where P is a final state. And initial state is S comma 0, where S is a start state. So this is the configuration graph. As you can notice, the configuration graph is infinite if the OC is not a finite automata. If it's a finite automata, you will get a finite configuration graph. Otherwise, it's an infinite. I hope so far it's clear. Okay. So here is an example of a configuration graph of this language A raised to n, B raised to n, A automata, DOCA. So as you can notice, the P's. So this is the state with state P and the configuration with state P and counter value 0. This is the configuration with state P and counter value 1, etc., etc. And here you can see the states Q, and this is state R, and the state S is basically the sync state, so shaded. So this is like this is the configuration graph of this DOC. So I hope this is clear. Now let's look at some properties here. So we'll always keep n as the size of the DOC we are looking at. So consider DOC with n states. Let P be some state there, and D is an integer which is less than or equal to n square, and I is greater than or equal to n cube. So now let's consider a sequence of configurations like this: Pi plus D, Pi plus 2D, etc. Okay, it's a long sequence of configurations like this. Now what happens? So as you notice, what is happening here? So it's the same state, but the counter values are D apart. Right? So I plus D, I plus 2D, I plus 3D, etc. It's a sequence of configurations. Now I take a letter A from these configurations. We get a sequence Q I plus C, Q I plus D plus C, Q I plus 2D plus C, etc. Where C is -1, 0, or 1, and state is and Q is some state. Right. So basically, what I'm saying is that like from Pi, you on A you go to Qi plus C, and Pi plus D on A you go to Q. It's clear, right? Basically, I like the Qs are the same. That's the basically two properties of the sequence. The states are the same, and then the counter values are again separated by D. So these are the two properties. Now we can extend this thing, and so we can say that for any word W, so take any word W where W is less than or equal to n cube. So basically any word of length n cube, and so any word of length n cube you take, then there is a state R and J, counter J, such that you from the sequence you take W, you're going to end up with a sequence where the state is R, basically the same state, and the counter values, the difference in the counter value is D. I hope this is also clear. Now, in particular, why is this n cube? Why am I saying n cube? That's because my I is greater than n cube, and it's not going to touch 0. Okay, as long as it does not touch 0, it is more like an finite automata, and this is basically the behavior is the same. So just to be clear for those who have not seen on-counter automata, so the behavior changes in an OCA when it touches 0, and when it touches 0, the OCA can check that the counter is, you can see that the counter is 0 and move in a different direction. I mean, it can decide a different direction, a direction which is different from when the counter is non-zero. So as long as the counter is since the counter is not touching 0 anywhere, you're going to get the same state. And yeah. So what is unique about this sequence? Basically, the states are the same, and the counter value. If you look at the counter value and you look at this remainder mod D, that's going to be the same. Okay, so J mod D and J plus D mod D, etc. They are going to be the same. That's clear. So now the question is that how many non-intersecting sequences are there? Okay. So the number of non-intersecting sequences are basically the number of states into D, because mod D, and that's ND, and which is like less than or equal to n cube, since we have taken D to be less than or equal to n square. So the number of non-intersecting sequences are less than or equal to n cube. Okay, so now this is one final thing which we want to just understand. So consider that there is a path from Pi plus n to q comma k.
Sorry, what is a non-intersecting sequence?
So basically two sequences which do not intersect.
These are sequences of the form P comma I plus D, is it?
Yeah. This is a sequence. A sequence is like this. These sequences which are sequence of this form.
Okay. And so what are you saying? The number of non-intersecting sequences?
Yeah, because what are we saying? So each a sequence is basically represented by a state and J mod D, the counter value mod D.
So for every P and every I and every D, I'll have a different sequence, right?
So starting, so this is, you can think of it as like an infinite sequence, and starting is like I mean like I n q plus 1 or something like that. So you can fix the starting.
Right.
So just forget about the starting, because the sequences are infinite.
Okay, but then for every D also I get a distinct sequence, right?
Yeah. So that is why
Oh, no,
number of
okay.
states
I
into
mean,
D.
okay, but they might intersect at
No. Number of states into D, because these are all D different. So R, so this is starting RJ plus D, etc. So the modulo D is what is important.
Mhm.
Okay. So if this is modulo D, this J plus D is, so let's say J is divisible by 0, D. Sorry, let's say J is divisible by 0. Then J plus D is also divisible by D. J plus 2D is also divisible by D.
Mhm.
Yeah. So the number of sequences are therefore this number of states into D, a non-intersecting sequence.
Okay.
Now, so we want to pick up these. Okay, so let's look at this. So let's assume that there is a path from Pi plus n to q comma k, and such that the run do not touch a configuration with zero counter value. Basically, in this run, you never see zero counter value configuration. So then we say that then there is a word w which is less than or equal to nq, such that you take you consider the sequence pi plus d, this thing. Uh, okay. Yeah, I think I just made one mistake. What is this person doing here? Um, it's an different. Okay, so just assume that this is a path from pi to q comma k with um, uh, yeah, I mean like there's a path from yeah. Now what we are saying is that there is going to be a path from pi plus d to this thing where, see, I mean you can reach this qk from this sequence with a word which is less than or equal to nq. That's the main idea. Now, how do we get there? So let's assume this pi, it's pi, and v is greater than nq. So what could happen is that so pi, you go, so since it is more than n cube, from pi See, there's going to be two configurations here on this path which have the same modulo d because it's greater than n cube. There are only n cube many things which have the which are different. So there has to be two configurations which have modulo d same. So now, therefore, now you can basically cut short this, which means that then there is a path from pi plus cd to directly to q comma k. Okay, so that's what we want. So basically, you are saying that you can reach something with a small word. Okay, so therefore now what therefore we can show is the following, that now you consider any sequence like this. If you simultaneously run like a breadth first search from all of them, you're going to hit all sequences in depth n cube. And now if you bound the number of elements in the sequence, then this entire this parallel breadth first search will run in polynomial time. So basically in n cube time, in n cube steps, you can basically get all non-intersecting sequences, and everything will run in polynomial time. So this is the crucial one important fact we should keep in mind. It's clear? Okay.
So sorry. So the non-intersecting so I guess if P and I are fixed, then there is only one non-intersecting sequence, right?
For
If P and I are fixed.
no, I is not like, okay, it starts from pi, let's say, then on A you will get some other thing, qj up to this thing, qj plus d, qj plus 2d, etc. So the sequences, you think of it as infinite. I mean, at least in this thing. Here we'll when this is polynomial, we are going to take a very large polynomial so that things will intersect. So to think about it, you are always assume that the sequences are infinite, and you don't want it to intersect.
Right.
So you
So,
start
okay, so I agree that for every P there are D distinct sequences.
Sequence starting, yeah.
I mean, because from I plus 1 I can again do D.
Another one, yeah.
Okay.
Exactly. So there is something which starts from pi plus 1, pi plus 2, etc. Yeah, and they are not going to intersect these data. And yeah.
So, and what is this breadth first search?
Yeah. So now what you are saying is that all sequences which we can find all sequences by a breadth first search, where you want to search only till depth n cube, because all sequences you'll be able to, all sequences which can be reached without touching zero, you can find with this parallel breadth first search. Okay. Because there are short n cube length words to reach any. So main idea is that here, which we have used, is that if there is a word which is more than n cube, if you notice here, let's say there is a more than n cube length word, then there has to be two configurations which basically have the same state, and the counter value modulo d has to be the same. And then you can cut short it. Basically, you can then start directly from pi plus cd, go directly here with u to RL plus cd, and then take v to reach qk. So you need not. So you can basically have a smaller word, a word less than or equal to n cube word, to reach from one sequence to another sequence. So from any sequence, you can reach another sequence in by using a word of length at most n cube. Okay. So therefore, if you run like simultaneously run a breadth first search from all these things, you'll get a sequence. You'll be able to identify all sequence in n cube depth.
Okay.
Now, so now, like if now the sequence is polynomially bounded, you can basically do this entire breadth first search and identify all distinct sequences in polynomial time. Okay, so this is one crucial important factor. So now we can go to our oil star algorithm. Yeah. So what are we trying to do here? So let's recap. So we have been the teacher knows a language which is accepted by a DOCA, and so we'll assume T is a minimal DOCA equivalent to teacher's DOCA, and N is the number of states of the DOCA. To make the presentation simpler, we are going to assume the following: there are no epsilon transitions, and in a transition the counter is incremented or decremented at most by 1. Now the learner wants to learn a DOCL which is equivalent to T. Okay. So how do our oil star algorithm look like? So initially we are going to assume the oil star assumes N, which is the size of the DOCA, which the teacher knows to be 1. So initially we assume N to be 1. Then the DOCL, so then it learns a DOCL. So that we'll describe it soon. It learns a DOCL, then that is checked for equivalence with teacher. If the teacher says L is not equivalent to T, then N is incremented.
L is of size N?
L is
of size 1 initially?
Yeah, so initially we are going to assume that, we are going to start assuming with the assumption that the teacher's DOCA is of size 1. N is equal to 1. N represents the size of the teacher's DOCA. Now, assuming that the OL star algorithm tries to learn a DOCA L, it will try to come up with some L. Now, if the teacher says L is not equivalent to T, then N is incremented. Now, this process continues with the incremented N.
So this L that you conjecture, will that be of size at most
N? No,
or
it
can be more?
It can be more.
Okay.
So finding the minimal DOCA is NP complete. So you can't minimize. So you'll never be able to ever get the minimal DOCA. However, you might get a polynomial approximation. So the process continues with an incremented N. Now, if the teacher says yes, L is equivalent to T, then we are done, because then we have learned the DOCA and the oil star terminates. So for proof of correctness, we have to basically show for two things. For every N, oil star runs in time polynomial in N, and when N is equal to the size of T, then oil star learns an equivalent DOCA. So we'll have to show this. So what we are going to do is that what we will now work with is that we are going to assume that we know the N, we know the size of the teacher's DOCA, the minimal DOCA, and then using that N, I'm going to try to learn a DOCA. Okay. So now, what is the first step? The first step is the following. So notice that the learner so we talked about the configuration graph, which basically has all the information of this DOCA key. But however, the learner do not have access to the configuration graph. It does not know about the counter values or the states or things like that, how are transitions, etc. But what the learner can do is the following. So here is a definition, which we call it a K behavioral graph. So A is a K behavioral graph if A is K equivalent to T. That is for K length words, A and T, they are the same. Now, what we can do is the following. So we can use Angloin's L star algorithm to learn a K behavioral graph in time polynomial in K and N. So for any K, Angloin's L star algorithm can be used to do this. This is where minimal equivalence is used. As we said, we are using minimal equivalence. Using minimal equivalence, Angloin's L star can be used to learn any K behavioral DFA. So step 1 of learner is to learn a poly-N behavior DFA. Now what this poly-N, we're going to fix later. But as you know, for any poly-N we can learn a behavioral DFA in polynomial time. So this is step 1. So we have learned the behavioral DFA, poly-N behavior. Next thing, step 2 is we take this DFA and we partition it into 3 regions. So there's this initial region basically consisting of all states reachable by words of length less than n raised to 4 from the start state. Then there is this border region which is reachable by words of length exactly by like uh, uh, border states are reachable by words of length n raised to 4 but not less. And then all the remaining states. So we have partitioned the behavior DFA into these 3 regions. So what is the first thing we noticed? First thing we noticed is that any path from the initial region to region of interest has to traverse through some border state. Next, our next idea is we
Sorry,
are planning.
Sreejith, what is K? What is the K you use here?
Where's K? Okay. So this P0 to PK will see.
No, I mean
we'll
you've
see.
learned a K equivalent DFA, right?
No, so we are learned the Paulian behavior DFA. That Paulian will fix, but that Paulian and K will match.
Okay,
So,
okay.
okay. Wait, I'll come to K soon. Sorry, not have been there. So in partial OCA construction, what we'll do is that I'm going to pick a border state P0. Now in this DFA, let's say I remove everything from border state except I just keep P0. This is called AP0. My aim is to construct a partial OCA LP0 that is Paulian equivalent to AP0. So AP0 and LP0 will accept the same language, intersection Paulian length words. So this LP0 is what we are planning to construct. And as you could notice, just to quickly, we can notice that if I have LP0, like for every border state, I have a partial OCA, then you can come up with a OCA which basically, which is equivalent to Paulian to A, right? So let's see how to do this, construct this partial OCA LP0. Okay. So just to recap, if this is my partial DFA, what we do is that we forget R0, Q0, we only keep P0. This is the DFA we want. Okay, so now this is the, now our aim is now to construct LP0.
So sorry, can you go back to the DFA partitioning?
So there is an initial region which is basically all words reachable from the start state by length less than n raised to 4. The border state reachable by n raised to 4 but not less. So exactly n raised to 4 reachable. And then, of course, you can reach it by greater than n raised to 4 words, but then the region of interest are basically everything other than that. Clear? Okay. So you can reach the region of interest only via border. From initial region, you have to go via border to region. Okay. Shall I proceed? Yeah.
So that is something that some new state that you reach when the length is equal to n to the 4.
It's that's a new
border
state. That's a border state, yeah.
Okay.
Okay, yeah. Now here's a definition. It's called as a winning sequence. We say this W0, W1, W2. So these are a sequence of words. We say it's a winning sequence if the run of these words on T reach configurations Pi, Pi plus D, Pi plus 2D, Pi plus KD. So there are K words, and then you're going to reach configurations Pi, Pi plus D up to Pi plus D. So basically the same state, and D is less than or equal to n square, and I is greater than n cube. So something similar to a sequence we saw earlier. So this is called as a winning sequence. Now the most an interesting thing is that this lemma, the winning sequence lemma, which says that for any state P0, so basically the P0 of the in behavior DFA, actually any border state P0 should have been not any state, any border state P0 in behavioral DFA we can give a winning sequence W0, W1 to Wk. This can be found in polynomial time such that the run of W0 on A reaches P0. Basically, W0 reaches P0 and then W0, W1 to Wk is a winning sequence. This is an interesting lemma which we are going to make use of. So we'll keep the proof of prove this lemma later, but let's assume this lemma that we have this lemma. How are we going to learn this? We're going to use it to learn a DOC. So consider a winning sequence W0 to Wk. Run these words on the behavior DFA. We reach the state sequence P0 to Pk. Right? Just run it in the behavior DFA. You're going to reach these states. Now what we do is that we are going to run this start a parallel breadth first search of at most n cube depth from this sequence. So we'll identify all distinct sequences, meaning sequences which do not intersect. And as we know, there are at most n cube distinct sequences. So we basically collect all these sequences. These distinct sequences are going to be the states of our DOCA, the learner's DOCA LP0. That's the main idea. You can see an example. So let's say this is our sequence. We have P0 to Pk. I take an A. We get a Q0 to Qk. So what we do is that we are going to construct a DOC here. Each sequence is going to become a state in my LP0. So this sequence becomes this sequence. The red sequence becomes a red state here, and the blue sequence becomes a blue state here. And there's an edge between them with A, and we are going to label it A greater than or equal to 0, 0. So there's no counter increment, and for any counter value you can do this. Okay. Now we take another transition B. It's a parallel breadth first search from the sequence. So 8 we took. So now we took B, and we get another sequence R0 to R. Now we added that state also. Now we took another. We are going to assume there are only two letters. So from Q0 to Qk, we took A, and we got the state T0 to Pk. Again, it's only coming. Now, when I took a B from Q0 to Qk, I did not get R0 to Rk, but I got, as you can notice, Q1 went to R0 and Qk went to Rk minus 1. So there is a shift in the sequence. This is not the, but this is an intersecting sequence, as you can notice. So basically, this Q0 goes to R minus 1. That's a state we can call R minus 1. But the sequence is from R0 to Rk. So what we now say is that from Q1 you can go to R0 with a counter decrement. So from Q, therefore, you're going to go with a counter decrement to R, and on seeing B, and the counter has to be greater than 0 because it's not from counter 0, it's from counter 1. You can take a B, decrement the counter, and reach R0. So that's this. Next, from R0 again, I take an A, we reach T1 to T. So from R0 it reaches T1, not T0, T1, and Rk minus 1 reach Tk. What do we do now? As you can guess, we increment the counter. So for on seeing A from any of this state, you increment the counter and reach the state T. I hope this looks fine. So now there's a self loop on B, and therefore we'll add a self loop here, and a self loop on A, we'll add a self loop here, and now there's something back. T0 goes to R1, T1 goes to this thing, so therefore T0, T, you get counter increment and you go. So I hope this algorithm is clear, what we are doing. So this can be formalized by the states of the partial OCSR sequences, and The transitions are as we described now. And what you can notice is the following in this here. What you can notice is that if there is a path from P0 here, it goes like this, comes like this, then there is a corresponding path here also. And second thing to notice is that if you treat P0 as a like a config like this as a configuration P and counter value 0, you can see basically a path from like so like what I mean is that so the run of this is kind of, it simulates the run of this DFA here. And there's a mapping from the configurations P0 here in this OCA and the P0 state here. And the configuration P1 here and the state P1 here. There's a mapping correspondence. So this is the
So this one counter automata that you've constructed will be again k behavior equivalent to the I mean, it'll
it'll be
to the automaton and to the
it will be Polyane equivalent. It will be Polyane equivalent because this automata is Polyane. So I take all the sequences up to Polyane. The sequences, but since there is a D difference, it might the number of states will only be k. But there are p like things p's in between also here, which might come here the loop and everything. So the word from here to here will be of k. A word from P0 to QK might be of length poly, which is what the DFA has learned. Let's say this is the topmost portion of the DFA, the behavioral DFA. The path from here to here will go through here and reach here in polygons. Okay. So so this is the idea here. Now you can notice that there are small things missing here. For example, the R-1 is not captured in this OCA. So we'll have to add these things in some manner. So that is so like in this parallel, most of the reachable states are colored now. But however, some n-cube number of states are not colored, which is basically the R-1 which we saw. There are small number of things. Because of this shift, what we can see is that because of the shift, there is a shift here R-1, and then you can have at most n shifts, and therefore some states might be left behind. So you'll have to add those things as an extra state. For example, you add that state here from Q on B on 0 value on 0 counter, you move to this R-1 state, and then you just loop here. So you can add those things extra without, just like a DFA state, you can add those things, and then you can also add edges from there back into this machine. So that's the idea. Now this is basically the idea. Now the initial region is added to the so right now we have treated only the region of interest and from P0, but now you throw in the initial region also into this DOCA, which we have constructed. Like this next stage, you can add that region also like a DFA without increasing anything. So these are like some little bit cosmetic surgery we can do and fix this thing. So this concludes the construction of partial OCA, the LPZ. Clear? What we discussed. So is it clear? So this is the main idea of this construction. Now
about 10 minutes left.
Yeah. So this is done. So now, as you can see, this so basically now this LP0 is equivalent to this LP0 is equivalent to the DFA with only P0, not the border state. Equivalent means Polyane equivalent to this DFA, and without the border state. However, now you can basically combine, if there are other border states, you can basically have LP, LQ, LR, etc. on these different things, and then you can combine them. And then what you get is that for any word W which is less than or equal to Polyane, you can get L accepts W if and only if A accepts W. So basically the DFA accepts W if and only if the OCA constructed. Now, how does it work now? Now, this is result by Baum et al. In 2013, which says that like there is a polynomial poly-n such that if L is poly-n equivalent to T, so basically L and T are OCS, DOCS. There is a polynomial poly-n such that if L and T are polynomial equivalent, then L is equivalent to T. So this poly n, which is in Baum et al., we are going to use here. So my automata A had basically has learned the behavioral DFA is basically a poly-n behavioral DFA, and therefore, due to this result, we have that L is equivalent to T. This concludes the proof of this concludes the oil star algorithm. Just to summarize, our main idea is to first the step one is to construct a poly-n behavioral DFA, then partition it into three parts: initial region, border, and region of interest. Now, for each border state, you generate a winning sequence of words, and then from that you get a sequence of states in the DFA, and then you run a parallel BFS. From this sequence, you get a lot of sequences. Each of these sequences forms states of the partial OCA, and based on the shift of sequences, we can add counter values. Then finally, you add some extra states and initial region to get this full partial OCA, and then we construct a final OCA by combining these partial OCAs. This concludes a summary of oil star. We'll now look at the proof of this winning sequence. That's
Sorry,
result. Yeah.
So Sreejith,
Yeah.
so can you go back to that that Baum's? Okay, so this poly-n, so there's some polynomial n such that if two OCAs are poly-n equivalent, then they are actually equivalent.
Yeah. So basically, if two OCAs are non-equivalent, there is a poly-n word which will distinguish them.
So for so starting with n equal to 1, n equal to 2, etc., you try to learn
yeah, something like it's the same algorithm and try to learn some OCA. And whatever we get, we basically give it to the teacher. The teacher says, "No, this is correct." Then we are done. The teacher says, "No," we increment them and go ahead. However, for the correct n, we will learn an equivalent DSA. Because for the correct n, I'm going to use the correct poly-n. Whatever the poly-n Baum has given us, we use that correct poly-n and learn the behavioral DFA of that size. Basically, do everything else.
So why is the whole thing poly time?
So because so okay. So learning the poly-n size DFA is polynomial. Each of the thing. Now, if you can notice here, learning the behavioral DFA is polynomial. Partitioning is of course polynomial.
So why is that polynomial? So Anglo's algorithm learns something.
Okay, partitioning is polynomial because you have this large. Let's say you have a k size DFA. I can find the minimal length words to each of this point. Like just a depth of search, you can run and find the smallest word which will reach each of these points, and then that way you can partition the states into based on the smallest word which takes you from start state to that state. Basically, because in partitioning we are identifying all states which are reachable by less than n raised to 4 words. So if the smallest word which takes me to that state is less than n raised to 4, okay, I'll put it into initial region. If the smallest word which takes me to state is exactly n raised to 4, I put it in a border state. Anything more than that, I'm going to put it in the region of interest. So this can be found out by a depth of search partitioning. Then winning sequence, as we'll soon see, it's finding out a winning sequence is also polynomial on the size of the automata and the sequence length. Then the parallel breadth first search, as we said, is an n-cube depth breadth first search. So that's also a polynomial. Then once we have this, we can basically, we have all the sequences. There are at most n cube many sequences. And then let's say I keep all the n cube many sequences there, and then I connect them by our edges. That's also polynomial. Then you combine multiple LP0, that's also polynomial. Yeah, these are all very bad polynomials, but this works. I mean, like, so the final OCA we construct is like n raised to 4 size OCA.
Okay, so this polynomial is like n raised to 4.
Yeah, the final OCA we construct will be of size n raised to 4. I mean,
No,
one can
this poly n is of what?
no,
What
no,
is
no, no.
the
Poly and the running time is going to be huge because
no?
this
This
poly n
poly
comes from
n, I mean
is,
this.
is coming from the equivalence, the results for equivalence. That is n raised to 20.
Mhm.
Because if
Okay.
someone comes up with a faster equivalence, this poly n will come down.
Mhm.
So Baum said that the Baum's result basically says like something like an n raised to 20 sized word can distinguish them. But however, everything tested, everyone believes. I think an n raised to 5 would be an ideal thing, but I mean we are not able to show 4 equivalence. But whenever that comes down, this result will get better. So this is basically directly related to the equivalence bound. This poly
So the size of the OCA that you learn is
n raised to 4.
okay.
That's because you can notice here. That's because the number of sequences, as we said, is only n cube.
Mhm.
The number of sequences is only n cube. So the number of states here is only n cube. Then you can throw in some extra states, which is also n cube.
Mhm.
Then the initial region is n raised to 4. You throw in that, you're going to combine everything. You're going to get an of n raised to 4.
Okay.
Yeah. Yeah. However, in the paper, we did not exactly calculate all these things because it's little, yeah, yeah. So in the paper, we do not even argue what is the correct size. I mean, like we do not argue the best size. We have a size, but it's not the best. But n raised to 4, maybe one can even try to work out an n cube thing, but we didn't try. Anyway, so now finally coming to the win sequence thing, which is a proof of winning sequence lemma. What is the idea? What's the problem? So basically, winning sequence is basically you have, see, for any border state P0 in the behavioral DFA, we can come up with a sequence of words W0 WK such that like that sequence will give me these words. If I run these words on the teacher's OCA, I'm going to get the configuration PI to PI. So you see that we don't even know the teacher's OCA. We're going to get them. In fact, this is little. I mean, we did not explicitly. I mean, like not mentioned correctly. There's a slight relaxation here. Actually, the correct thing is that we don't directly get one sequence PI to PI plus C. We get actually polynomial number of sequences. Out of that, one of them will be a winning sequence. We are able to show that. So that's exact lemma, but it becomes a little tricky. However, this lemma is also true, but in a very twisted manner. Uh, but uh, but in our paper, what we show is that there are polynomially many words sequences like this, word sequences like this. Out of this, one of them is going to be a winning sequence. Okay. So let's say how what is the idea here? Here it's going to be not that difficult. So this is the crucial thing, the idea here. So consider start state. I mean, let S0 be the start state. Consider configuration PI, and let W be the lexicographically minimal word which takes me from start state to PI. So what is lexicographically minimal word? So it has to be the lengthwise, it has to be the smallest word. And among all the lengthwise words which will take me from start state to PI, I want it to be in a lexicographical order to be also smallest. So this is a unique word. So it's a unique smallest word you can think of it. Okay. So this is my WS LX lexicographically minimal word which takes me from start state to PI. What is good thing about that? Now what we can show is that if we have a PI whose configuration where the counter value is greater than NQ, then this is of this form. LXPI is of the form X y raised to RZ, where X, Y, and Z are bounded, and Y increases the counter by at most n squared. Furthermore, if you now pump Y, you're going to get a same state PI plus JD. So this is what we want to prove. So how do we prove this? So let's consider W to be Lex PI. Now, in fact, okay. So W be this thing and C. Okay. So what we do is that let's CA is the configuration. So now you've basically taken the run of this word W. Let's denote by CA the configuration where counter value I is seen for the last time. CA is the configuration, counter value I is seen for the last time. So you have CI, CI dash, etc. However, the number of the counter value is more than n cube, right? Because here PI, I is greater than n cube. So actually, so therefore, what we have is that, sorry. So since they are greater than n cube, what we have is that we have two states CI and CJ, which are same, and two states CI dash and CJ dash, which are same. They are the same state here and here. This is the same word, W. So CI here and CJ here are the same state, CI dash here and CJ dash is the same state. Now, once we have that, we can write the word like this. Let's say this part is Y. However, this word U is the same as this word U. Why is this word U same as this word U? Because this goes from CA, same state to CA dash, and this goes from CJ to CJ dash. And therefore you have the same U here, and then you can basically form a pattern like this. Since this is Y, so this part is Y, and this U is the same. This initial part is Y here, then you can copy this Y here, then Y is same here, same there, same here, same there. So you get this Y here. Now, so this, therefore, you can argue that, so you will be able to show that the length of x1, x2, y, z1, z2, they are all bounded by, one can show, and then y increases the counter also, that also we can bound, etc. So we can bound all these things and you get this. Now, as you can notice, it's also clear that if you pump y up, you're also going to get same p. So this is the idea here, and based on this we can get this. So now what we know is that W0 is going to be my Lexmin word. It's of the form x y raised to rz. However, I don't know this partition, how x and y and z are partitioned. So I don't directly have a pump, but I can try multiple pumps and generate multiple PIJ. So that's how I can have multiple sequences from which I can get different state sequences. I think that's it's not that difficult. So this way we can. This is basically the conclusion. So we skipped epsilon transitions, but that can also be taken care of with the same technique. So corollary, we also have a minimization for DOCA, an approximate minimization, because we get a DOC of like n raised to 4 size. And some future work is basically, can I replace minimal equivalence with an equivalence query? Secondly is that can we basically make this thing practical, the oil star algorithm. On major bottleneck is improving the running time of equivalence. So that's the hardest job here. And then what about weighted models like weighted visibly OCA, where equivalence is known, so maybe one can try learning it. Thank you.
Thanks, Sreejith. Any questions?
So, Sreejith, Madhukar here again. You had mentioned that, just now you said that, you want to replace the minimal equivalence by equivalence. The same complexity, right? So why exactly do you want to?
Minimal equivalence. No. So it's because for our running, because here we crucially use the minimal equivalence fact. So so if I want a poly and behavioral DFA, we want a minimal equivalence here.
Okay.
Because you see what happens is that you can see me, So see, an OCA could have a behavior like this. So on one, like it's basically a DFA like here, but then once it comes to counter value 0, so it's like an OCA. Let's say an OCA, like let's say A raised to n, V raised to n, it does it. Then it reaches counter value 0, and then its behavioral could be an entirely different OCA after it hits counter value 0. So it's basically two OCAs sitting together in one OCA. You can think of it.
Okay.
Now, so if it's a minimal equivalence, we'll be able to detect this poly and behavior for both the things. If it's only equivalence, maybe it will just keep on giving a counterexample to one-sided, the one part of the OCA and not the other side. So we'll just learn one part. So one has to, our ideas have to be, may not work, or maybe it has to be fine-tuned to get this thing out. Yeah. So as of now, we are not able to prove.
Okay.
Complexity wise is the same. Yeah.
Okay. Yeah. Thanks.
Thank you. Yes.
So is there a so for a given OCA, and let's say I have some value n, which is okay, some other value k. So if I have to find a DFA that is k equivalent to the OCA, is there some bound on the number of states that DFA will have?
Yeah, because you see the configuration graph, has only like an n. So let's say the number of states in the OCA is n, and you want a k equivalent thing. Then an nk size configuration graph is always there. So as you can notice, the configuration graph is basically we have some picture here. Yeah, I think here we are.
Okay, so nk is a bound
So
on.
you put like all states here at 0 counter, so one counter, 2 counter, etc. And like a k length path will be here, right? We'll have at most k, the counter value will be at most k. So there is always an nk size DFA which can recognize it. But there could be small.
So the problem isn't going from that nk sized automaton to, a maximum nk sized automaton to a OCA that is k equivalent to this.
Yeah, and also so the thing is that why don't we just use the okay, I can just call this DFA itself as my OCA, right? Because this is k equivalent. However, then it will violate. So this poly to n we have here. So we didn't say this poly n is based on the size of this L and T. This is a polynomial on the size of L and T. So since we know that L, which we construct, is of the size n raised to 4, that's why we have this polynomial. So, is it clear?
So that poly n depends on not just on T but also on L.
Yeah. So basically, on two OCS we are giving, and two OCS we are giving, and we are asking whether they are equal. It's based on the input size, right? So the input size is size of L and size of T. So this poly n, the poly n therefore is of size of L and size of T. However, L we know is of size n raised to 4. Therefore, we have like a poly n. So we still have a poly n. But still we have a polynomial.
Okay. Any other questions? Okay, so then let's thank Sreejith for an excellent talk and excellent work.
Thank you.
Thanks, Sreejith.
Thank you. Thank you. Yeah. Thank you.